Okay. Let's get started on the exam. So the first question should have looked very similar to what you had in your first lab, where the purpose here was to get you comfortable dealing with exponents and using your calculator to use the EE or the E key or the 10 to the key or however your particular calculator works. So if you were, that was the purpose of this first one. So if you were able to work your calculator properly and do the order of calculations, then you should have gotten A as the answer. The second one has a bit of a calculation to it. So once again, this is similar to what you would have done in that lab where you're working with density. And so here we were told that the density of methanol is 0.791 grams per mil, and that we had 164 grams of methanol. And then we wanted to calculate how many mils of methanol that would be. So needed to think about dimensional analysis. So if we are in grams and we want to switch to mils, we use this conversion, grams per mil density value, to make that transition. So we wanted to have grams in the denominator, mils in the numerator. So then the grams cancel. And then if we do the math, we get 207. We get 207 rather than 207.332 because we have 3 significant figures in our density value and also in our weight. So we want 3 significant figures in our answer. Okay, 3, which elements, names and symbols were correct? The answer was C, sodium's Na, potassium is K. The others have something wrong. So in the first one, Fe iron and Ti tin, what's wrong with that one? Does anyone know?
Tin is Sn.
Right, tin is Sn. How about the second one? C carbon, B barium.
Barium's Ba.
Barium's Ba, right. And then the last one, fluorine, F, and aluminum A.
Al.
Al, yep, Al is aluminum, great. Then the fourth one, which is an intensive property. Intensive is the one that's independent of how much stuff you have. And so color is the answer for that one. 5, hypothesis, tentative model that describes underlying cause of physical behavior beyond observations. Scroll up here. That was a true false. That is false because remember the hypothesis, hold on. So the hypothesis isn't after you have more information. So this is describing a theory. 6, if matter is not uniform throughout, is classified as a heterogeneous mixture is the answer there. Most prevalent element in the human body, that's oxygen. My favorite separation technique, I don't think anyone missed this, but it's chromatography. Kinetic energy, energy of motion. prefix K for kilo, that's 10 to the third. So number 11, another dimensional analysis type problem where had an amount of gold, 0.0692 grams, and wanted to convert that from grams to micrograms. You needed to remember that micrograms were 10 to the minus 6 grams. So if we set that up where we have grams in the denominator and micrograms in the numerator, the units will cancel out on the grams, and we'll be left with 6.92 times 10 to the fourth. Number 12, the last class I had some questions about this, where we have these two numbers that are added. The key here was remembering the significant figure rules for adding and subtracting. And for those, what determines the significant figures are the number of digits to the right of the decimal. So the 14.3505 had 4 digits to the right. The 2.65 had 2 digits to the right. So that 2.65 value, that determines how many significant figures you have to the right of that decimal. And so the answer is 17.00. If it was multiplying and dividing, then it would have been the number with the least number of significant figures, and it would have been 3 because 2.65 has 3. Number 13, sound travels at the speed of 768 miles per hour. How many meters does it travel in 1 day? And then you were given the conversion that 1 mile rather equals 1609 meters. So what you needed to do is you needed to convert miles into meters and then hours into days. So in the numerator there, we have 768 miles times 1609 meters per mile. So our miles cancel. That gets our units into meters. And then in the denominator, we have 1 hour times 1 day, 24 hours in a day. So the hours units cancel, gets us into days. And then if we do the math, we get 2.97 times 10 to the 7th meters per day. Uh, 14, total mass of substances present at the end of a chemical process is the same as the beginning. That's law of conservation of mass. That's one of the things we're going to be talking about today. So that law of conservation of mass is big in balancing equations and stuff, which is what chapter 3 starts to talk about. In Dalton's view, the electron was the smallest particle possible. That was false. He thought it was the atom, and that was actually one of the weaknesses in his theory. Cathode rays. Someday I'll learn to work the Apple mouse. Probably not in your lifetime, but.
You could try grabbing like the sidebar and slowly pulling it down. It's kind of hidden.
Yeah, okay, here we go, thank you. As you can probably tell, I'm not a Mac person at all. Okay, cathode rays, negatively charged particles. Those particles became known as electrons. The 3 types of radiation, which has the highest penetrating power, that's gamma. Accuracy refers to how close you are to true value. Oddly enough, that is true. Nucleus of the atom contains protons and neutrons. Angstrom is 10 to the minus 10th meters. When two particles have similar, which two particles have similar masses? That's the proton and neutron. Remember, we said electron contributes very little to the mass of the atom. Atomic number tells us how many protons it has. That's true. Isotopes have different masses. That means they have different neutrons. The protons stay the same because that tells us what element it is. Group 1A are the alkali metals. In 25, if the molecular formula is C6H4Cl2, then the empirical formula, what would the empirical formula be? This is false, but what would it be?
C3H2Cl.
That's right, C3H2Cl. So that molecular formula, that C6 molecular formula, is divisible by 2. 26, which common cation does not have a +1 charge, and that's calcium. All the other 3 are +1 charges. This compound is named ammonium sulfite. That's incorrect. It's sulfate. SO4 is sulfate. HClO3 is chloric acid. Prefix hepta stands for 7. N2O4, someone had asked me about this. It's dinitrogen tetroxide. It's not dinitrogen tetraoxide. That's that double vowel rule where with the A from tetra and O from oxide, you don't have the double vowels there. Okay. Alkanes contain carbon, hydrogen, oxygen atoms. That's false. Alkanes are just carbon and hydrogen. And then finally, a kinetic energy calculation. So here we were given the kinetic energy formula, 1/2 times mass times velocity squared. And we wanted to calculate that kinetic energy in joules. So there's a couple of things we needed to remember. One is looking at the note saying that joule, units for joule is also kilogram meters squared per second squared. And that tells us then that our mass, in order to match up with those units, has to be converted to kilograms. And it tells us that our velocity needs to be in meters per second. So if we look at the data that we're given to work with, we have 4,127 grams. So that has to get converted to kilograms. And so we multiply that by 10 to the minus 3. So we slide the decimal place over 3 times and we get 4.127 kilograms. The velocity is already in meters per squared, so we're okay there. We just have to remember to square that term. So we do that conversion of the grams to kilograms. We have our velocity squared and then multiply it all by 1/2. And then we get 51.61 as our answer. So like I said, class did pretty well in the exam in general, so that's great. But any questions on the exam before I move on to chapter 3? Okay, so let me pull up chapter 3 here. Any idea why that doesn't come up on the screen?
Does what?
It doesn't come up on the screen. So the sharing people see the slides, but in here we get that.
Maybe we use slideshow.
See, I don't get that. Okay, I'm just going to go on. All right, so in chapter 3, what we're talking about are chemical reactions and reaction stoichiometry. And as I said, some of this is pertaining to what you're doing did in the lab a little bit last week. So when we talk about stoichiometry, what we're talking about, it goes back to that law of conservation of mass. And remember what we said is in a chemical reaction, the number of atoms and types of atoms that we have in the reactants have to carry over into the products. Now they can rearrange so that you have different compounds, but we're not creating more atoms and we're not destroying atoms. And so what we do in this is we try and explain what those reactions look like. When we talk about studying reactions, we write what we call a chemical equation. And so if we look at this example here of H2 plus O2 going to H2O, there's some things I'll point out. One is the things on the left, in this case, the H2 and the O2 are the reactants. The things to the right of the arrow, in this case, the H2O, those are the products. And the arrow tells us what direction the reaction's going, so it's going left or right. Sometimes you'll see an arrow going back to the left, so a double arrow, one going each way. That indicates that there's some type of equilibrium going on. So you've got some things going to the products and some things staying in the reactants. This indicates that the reaction will go all the way and the reactants will be used up and go to the products. On the left, we see where we have two reactants. We put a plus in between to show that those two are going together. Those are if we had a third thing, there'd be another plus and then that molecule as well. Some of the things you'll also see is you'll see a coefficient in front of the H2 and in front of the H2O, that number 2. That tells us there's 2 of those molecules in the reaction. And this, we'll talk about this in a bit more when we talk about the balancing of the equations. So we said that balancing equations links back to that law of conservation of mass. It tells us that we want to have the same number of atoms in our reactants as we do in our products. So if we have 2 carbon atoms in our reactants, we need to have 2 carbon atoms in the product. They may be in different molecules, but they're in there somewhere. So what we do to make this happen is we do what we call balancing equations. And that's what those coefficients in front of the molecules do. They allow us to balance it out. The other thing I'll mention is that if it's just one of the molecules, we don't write the number 1. That's implied. So we only write things that if it's 2, 3, 4, some number other than 1. If we look at this example here down at the bottom where there's methane plus oxygen plus CO2 plus water, we can always tell if the reaction is balanced or not by just doing the adding up. So if we look on the left-hand side, we see there's 1 carbon atom, that's from the methane. And we look on the right-hand side, the product side, and we see 1 carbon atom there. So the carbon's balanced. If we then look at the hydrogens, we see we have 4 hydrogens on the left, and we have on the right 2 for water, but we have 2 of those water molecules, so 2 times 2 is 4. So we have 4 hydrogens on the right, so that balances. And then the final is oxygen. On the left-hand side, we have O2, but we have 2 of those molecules. So once again, 2 times 2 tells us we have 4 oxygen atoms. On the right-hand side, we have 2 sources of oxygen. We have the CO2, so we have 2 oxygen atoms there. And then we have water, H2O. So that's 1 source of oxygen, but we have 2 of those molecules. So 2 times 1 is 2. So the 2 from the CO2, the 2 from the 2 water molecules, that gives us 4. So one interesting thing about balancing equations is, so when you get that on a homework problem or test or quiz or something, and you're trying to figure out the balancing, you'll know at the end whether you got it right or not, because you can go back and do what we just did here and kind of add up the different atoms on each side. So if you've added them up and they're equal, then you know you got that problem right. Now, you may get confused as to how you get to that point, but once you get to the final thing, it's pretty easy for you to check your answer to see if you've got the right one or not. Let's talk a little bit about the coefficients versus the subscripts to make sure everyone's clear on what that difference is. So here we have a couple of example calculations, or rather example reactions, where we have H2 plus O2 forming water, and then H2 plus O2 forming H2O2. So in each case, we're reacting H2 and O2, and in each case, the reactions are balanced. In the first one, we have a coefficient in front of that to indicate that there are two water molecules. If we would have just changed the subscript on the oxygen, as they did in the second reaction, we would balance, but the problem is instead of making water as our product, we would make peroxide as our product. Those compounds, as you know, are very different. And so those subscripts on the molecules impact what the compound is. And so we don't want to change those. The coefficients on the front just change how much is there. So how many molecules are there, or how many moles are there, or things like that. It doesn't impact what the molecule is. So that's important to remember. When you go to balance equations, once you know what that equation is from a chemistry reaction perspective, you can't change the subscripts, because then you've changed the compounds that are in that reaction. We can only change the coefficients out front. Okay, we just talked about this, but let's go through it again and make sure everyone understands. Up top, we have the unbalanced equation. So this is methane again, plus oxygen, going to CO2 and water. So we're going to, remember, add coefficients in order to balance. We're not going to play with the subscripts, just the coefficients. So in general, when you do these types of things, the first thing you want to balance is one that is just in one molecule on each side. So in this case, let's start with carbon. That meets that criteria. So we have one carbon in the CH4 in the methane. We have one carbon on the right-hand side in the carbon dioxide, the CO2. So our carbons are already balanced, right? We have one on the left, one on the right. So we won't do anything to that. Now let's take a look at either hydrogen or oxygen. Well, in general, when you have something like the oxygen, the O2, where there's no other atoms in there, you save that for last to balance. That's kind of like an easy way to fix things at the end. And so instead of balancing the oxygens next, we're going to balance the hydrogens. So on the left-hand side, we have one source of hydrogen. That's the methane, CH4. So we have 4 there. On the right-hand side, we have one source of hydrogen. That's H2O. We have 2. So if we have 4 hydrogens on the left and 2 on the right, what do we need to do to balance that? Right, multiply the H2O by 2. So we put a coefficient of 2 in front of the hydrogen. So now we've balanced our carbons, 1 on each side. We've balanced our hydrogens. We have 4 on each side. And we did that by putting that coefficient 2 in front of the water. Now the only thing left to balance is the oxygen. Well, let's look at the right-hand side here. We have 2 sources of oxygen. We have the CO2. We said that coefficient is 1, so there's 2 oxygens that come from there. And then we have the water. There's 1 oxygen in water, but we said we're going to have a coefficient of 2 in front of that. So there's 2 oxygens there, 1 from each of the water molecules. So we have 2 from the water, 2 from the CO2 for a total of 4. The oxygen is O2, so if we have a coefficient of 2 in front of that, then 2 times 2 will equal 4. And then that'll balance our oxygens out. And sure enough, at the bottom of the page, we see that that's the balanced equation. So that's kind of the general process you go through to balance. So let's talk about those guidelines again, just so everyone's on the same page. If the element occurs in only one compound, do that first. So in this case, we chose carbon to do that. If it's the free element, in our example, it was oxygen. And by free element, it just means that in that molecule, you don't have any other atoms, just one of them. Then we'll save that for last, because that makes it a little easier to balance things at the end. When we are balancing, we're just using coefficients. That's the numbers in front of the molecules. We're not touching the subscripts, because if we touch the subscripts, then we've changed the actual chemistry of it. We haven't just changed the amount, we've changed what the actual molecule is. Another thing which we haven't talked about, but what you want to do is we don't have fractions. And by that is you won't have, say, half of an H2O or things like that. You always want whole numbers. So if for some reason you wind up with fractions, you need to multiply by to get rid of that fraction. Okay, here's an example that we can try where we're going to try and balance propane reacting with oxygen to form carbon dioxide and water. You're all familiar with propane. This is what was in the Bunsen burners that you were using. And so that equation is C3H8 plus O2 going to CO2 and water. So if we think back to our rules and kind of how we did the last one, let's go ahead and balance the carbon first. We look on the left side, on the reactant side, and we have one source of carbon, that's the propane. We have 3 of those. On the right-hand side, we have one compound that has carbon in it, the CO2. We have 1 of those. So if we want to balance that, we have 3 on the left, 1 on the right. We'd want to add a coefficient of 3 to the CO2 so that then we have a balance of the carbon. We have 3 carbons on each side now. The next thing we're going to balance is the hydrogen. We're going to save that oxygen for last because of that guidance of it's a little easier if you save the compounds that just have 1 atom in them for last. So we did carbon, now we're going to do hydrogen. So we look on the left and we see we have 8 hydrogens there in the propane. And on the right, our only source of hydrogen is the water molecule. And we have 2 of those in there. So we have 2 on the right, we have 8 on the left. To get that right side to balance, we'd want to have 4 as the coefficient for the water, because then 2 times 4 is 8. And that gives us 8 hydrogens on each side. So we feel good now. We have the carbons balanced with 3 on each side. We have the hydrogens balanced with 8 on each side. Now the final thing to do is to go ahead and balance oxygen. So if we look on the right-hand side, on the product side, we have a coefficient of 3 in front of the CO2. So 3 times the 2 oxygens tells us there's 6 oxygens coming from there. We look at the water and we have a coefficient in front of the water molecule of 4. So 4 times 1 is 4. So we had 6 oxygens coming from the CO2, 4 oxygens coming from the water. So that's a total of 10 oxygens on that right-hand side. On the left-hand side, the reactant side, we have 1 source of oxygen, that's the O2. So we need to have a total of 10 oxygen there. So if we have a coefficient of 5 in front of that, 2 times 5 is 10, now we've balanced out our oxygens as well. And that gets us to our final balanced equation of 1 of the propane molecules, 5 of the O2, reacting to form 3 CO2 molecules and 4 water molecules. So that's kind of the stepwise fashion you'll do when you're balancing these equations. Does anyone have any questions about this? Okay, so there's some homework problems I'd like you to work on. Couple things. One is, after you finish it, after you finish balancing the equation, you can check it yourself. That's a good habit to get into. And then you'll know if you have it right or not. The other is that you always use the smallest coefficients that balance the equation. Usually that works out normally, but sometimes it may not. But just as we don't want fractions, we also don't want like C4, one coefficient has a 4, and then a 4, and then an 8, and a 4. That'd be a case where you could divide all that by 4 and get it to a lower set of coefficients. Okay, let's talk a little bit more about writing the reactions. And so when we write those chemical equations that represent our reactions, there are some symbols that you'll see, and I want to just make sure you understand what those mean. So in this, you see that each of these compounds has a small g in parentheses. The G just means that it's a gas. If it's a small L, that means it's a liquid. If it's an S, it's a solid. People typically use the G and the S. They don't always use the liquid. A lot of times that's implied. But if you do see the small L, it's a liquid. The other one is sometimes they'll have a small AQ. That means it's an aqueous or water-based solution. Once again, not always used, but sometimes it is. And so that gives you a feel for what the state of matter is in the reaction. You know, the reaction that they have an example of here, methane plus oxygen going to carbon dioxide and water. Well, you know, the methane, the oxygen, the CO2, a lot of people know those are gases, so it's not as critical to write that G there for those. But water, that could be a liquid, it could be a vapor. So that's good that they wrote G there for the water, because now we know it's in the gas phase. And this ties back to when we were talking about the states of matter earlier in the semester. The other symbol that's on this reaction that I'll just mention is that little triangle that's above the arrow. That is a sign that some heat is used in the reaction. So in other words, energy, heat is introduced to make the reaction go. A lot of times when there is that, they'll actually list the temperature as well. Okay, when we talk about chemical reactivity, there's combination reactions, there's decomposition reactions, and there's combustion reactions. There are 3 general types. We'll talk about those a bit here. So combination reaction, which is really common, there's literally millions of these reactions out there. It's when you have 2 or more substances that react together to form a product. And so here's some examples here. You know, here they're talking about combination reactions that just form one product. You can also have combination reactions that form more than one product as well. We're not going to get into that too much here, but that's another possibility. If it's a combination reaction between a metal and a non-metal, you need to think back to the charges of things, and that'll help you know what that reaction is. If you think back that first column, that 1A column, those are all +1s, 2A is +2. You go over to the right side in the non-metals, you have fluorine, chlorine, those halogens, those are -1. So remembering some of those charges from the periodic table work we did comes in handy in kind of predicting what these are going to look like. And here they have an example of magnesium and oxygen down at the bottom. Decomposition reaction is when something decomposes into a couple of compounds. The one that textbooks love to have is the airbag one. And so the sodium azide, the way that works is it's the energy that gets put into it from the force of the accident. And then that triggers a decomposition reaction, and the sodium azide decomposes, and it gives off really quickly a lot of vapor, and then it inflates the airbag. So there is a formula here, a reaction here, calcium carbonate going to calcium oxide and CO2. Is that reaction balanced? So if we want to see if it's balanced, the first thing we would do is we would say how many calcium atoms are on each side. And we see we have one on the left and one on the right. Then let's look at the carbon. We have one carbon atom on the left. We have one from the CO2 on the right. And the third thing we'd look at is the oxygen. We have 3 oxygen atoms on the left. And then on the right, we have 1 from the calcium oxide. We have 2 from the carbon dioxide for a total of 3. So we've got 3 there. So here's a case of where we have a balanced reaction and we didn't have to add any coefficients to any of the molecules. It just balances out. And remember that little delta is heat. Okay, another type of reaction is combustion reactions. And combustion reactions usually involve oxygen from the air. And let's take a look at a couple of these. Here's propane reacting with oxygen to give us CO2 and water. And then methane reacting with oxygen to give us CO2 and water. Once again, if we wanted to check if these were balanced, we would go back like in the first one, and we would say 3 carbons on the left, 3 carbons because of the coefficient on the CO2 molecule on the right. We'd look at hydrogen. We have 8 hydrogens on the left. We have hydrogen source on the right of water. 2 times 4 is 8, so that balances. And then finally oxygen. We have 10 oxygens on the left, 2 times 5 on the O2. And then on the right, 2 times 3 from the CO2 is 6, and then 4 from the water molecules is 10. So we can check quickly to see if things are balanced. And here it is. We'd find the same thing if we went and did the second equation. So there's a combustion reaction that probably people use every day. Does anyone know what it is? It's the burning of gasoline in your car. So that's probably the most well-known common combustion reaction is in your car, you're burning the fuel in a combustion reaction to be able to generate the energy to drive the car, move the car. Okay, let's talk about formula weights and molecular weights and stuff like that for a little bit. And this is starting to get into some of the stuff that was in that lab last week. So the formula weight is the sum of the atomic weights for the atoms in that molecule's chemical formula. And so this quantitative thing, if it's for the element, it's the atomic weight. If it's for the compound, it becomes the formula weight or the molecular weight. Those terms tend to be kind of used interchangeably. So for the example here, we're going to determine the formula weight or molecular weight for sulfuric acid, H2SO4. So what we would do is we see how many hydrogen atoms are there, and that answer is 2. Then we'd multiply it by the atomic weight of hydrogen. And remember, we can get atomic weights off of that periodic table. That's some of the information that is on the periodic table. So that gives us 2 times the atomic weight of hydrogen, and then plus the number of sulfur atoms. In this case, it's 1 times the atomic weight of sulfur, then plus the number of oxygen atoms. So there's 4 oxygen atoms in this molecule, so it's 4 times the atomic weight of oxygen. The next line just fills in what those atomic weights are. AMU and grams are pretty much interchangeable, okay? Technically, you say AMUs, atomic mass units, but it's the same as grams. So don't get confused if you see AMU versus gram. And so here what we have is we have 2 times 1 in the, for the weight of contributed by the hydrogen atoms, 1 times 32.1 for the weight contributed by the sulfur atom, and then 4 times 16 to give us the weight contributed from the oxygen atoms. If you add all those up, in this case it's 98.1, that's the formula weight or molecular weight of sulfuric acid. So once again, if you have a compound and you're trying to get what that molecular weight, what that formula weight is, you need to know which atoms are there. You need to look up or be told what their atomic weights are. And then you need to multiply those atomic weights by the number of atoms that are in that molecule. So if this was in a chemical reaction and there was a 2 in front of that H2SO4, would I double everything to get the molecular weight, the formula weight? No, I would not. Formula weight, molecular weight is just for the compound. Okay, remember that 2 coefficient in front of the molecule in a reaction, that's just telling us how many of them there are. It's not telling us anything about the molecule. It's just telling us the numbers that are there. There's 2 molecules, 3 molecules, 1 molecule, whatever. So formula weight, molecular weight, terms kind of used interchangeably. That's atomic weight of the particular atom times the number of atoms that are in there. So that's that subscript. That's what we're doing there. So it's the subscript times the atomic weight of the atom. We do those individually for each of the atoms, then we add that up, and then that's the total weight. Same thing we talked about with formula weight is the exact same thing for molecular weight. It's essentially the same thing. So here we have glucose, C6H12O6. So to get that molecular weight, let's do carbon first. So we would look up the atomic weight of carbon, that's 12, and we know there's 6 carbon atoms here, so that contribution would be 6 times 12. Hydrogen, we have 12 hydrogen atoms. The atomic weight of hydrogen is 1, so it'd be 12 times 1. Oxygen, we know there are 6 oxygen atoms in this molecule because the subscript is 6, so it'd be 6 times the atomic weight of oxygen, which is 16. The thing I will tell you about these atomic weights, sometimes you see them like this, where they give you 1 digit past the decimal place. Sometimes you'll get it where there's no digits past the decimal place. Sometimes you get it where there's 6 or 7 digits past the decimal place. It just depends on how accurate your calculation needs to be, what you're doing here. There are some things that you need to be amazingly accurate on this, and that's where you'll have a lot of the decimal places. Typically for normal work, you'll have 1 or 0 digits past the decimal place. And so what I would suggest is when you're getting those numbers, if it's a problem and you're giving what the atomic weight is, use that number as they give it to you. If not, look it up in a table or the periodic table and use what that is. Yes?
So putting a number in front of the molecule doesn't affect the molecular weight or the formula weight?
That's correct. Yeah, so the question was, does putting a number in front of the molecule, so a coefficient in front, does that affect the molecular weight or the formula weight? And the answer is no. Molecular weight, formula weights are just dependent upon the number of atoms that are in the molecule, whereas the coefficient is telling us how many of those molecules we have in our reaction. And so for me, the easiest way to remember is when you're figuring out the molecular weight or the formula weight, you're concerned about the subscript numbers. That's what you're using, subscript and then the atomic weight of the atom. Okay, there's something else that is sometimes calculated, and that's percent composition. Excuse me. And in percent composition, you want to know what percentage of mass a particular, say, atom contributes. And I think this is one of the things you were asked to calculate. I think in the lab it was the theoretical copper, if I recall. So what you do is, first of all, you need to calculate out what the molecular weight of the compound is. So just as we talked about before, molecular weight we get by looking at which atoms are there and knowing their atomic weights, and then how many of each of those atoms are in that molecule, multiplying the number of atoms times the molecular weight for each of the different types of atoms, and then adding that all up to get our total. That total is your molecular weight of the compound. So that becomes the denominator in this equation. In the numerator, we want to know for whichever atom we're looking at, we want to know how many of those atoms are there, and then we multiply the atomic weight by the number of those atoms. Then that ratio is what we're doing. Since it's a percentage, percentages always, if something asks for a percent, that always means that you multiply by 100. So you get that ratio, number of atoms of the element that we're interested in times that atomic weight, divided by the molecular weight for the compound, and then to change it into a percentage, we multiply by 100. So here's an example for carbon and glucose. So if we want to know the percent carbon in glucose, we know there are 6 carbon, 12 hydrogen, and 6 oxygens. So to get that molecular weight, we would have 6 times the atomic weight of carbon, which is 12, we'd plus the number of hydrogen atoms, 12, times the atomic weight of hydrogen, which is 1, plus the number of oxygen atoms, which is 6, times the atomic weight of oxygen, which is 16. And then we would add those 3 numbers up to give us the total, and the total is 180. That would be our denominator, that molecular weight for glucose. Then to find out that what the carbon percentage is, we know there are 6 carbon atoms present. So we would have 6 times the atomic weight of carbon, which we said was 12, and that would be in the numerator. We divide that carbon number, that 72, by the 180, and then times 100 to make it a percentage, and we get a final value of 40.0%. Okay, any questions about either calculating a molecular weight or doing a percentage? Okay. So there's some homework in the book pertaining to these types of calculations. I would suggest that you spend some time looking at that. Okay, let's talk about Avogadro's number for a little bit. Avogadro's number is 6.02 times 10 to the 23rd. Now, you'll see it written where it has more digits past the decimal point than 0.02. That's fine. You can use as many digits as you want, but typically, just remember 6.02 times 10 to the 23rd. As you can see in bold red letters at the top of the screen, memorize this number, okay? You should know Avogadro's number is 6.02 times 10 to the 23rd. So when we talk about reactions and things like that, we rarely talk about individual molecules because they're just too little. And so this is where Avogadro's number comes into play. So there's something called a mole, and that's the amount of particles in 12 grams of carbon-12. The number of atoms, molecules, particles, etc., in 1 mole is 6.02 times 10 to the 23rd. And that's where this Avogadro's number comes from, is it allows us to operate in moles. And in chemistry, when you do reactions, you almost always talk in moles. You don't talk about grams, you don't talk about milliliters or anything. The reactions stoichiometry is such that you're talking about moles. And if you think back to that balancing the equation stuff that we were talked about earlier, those coefficients in front tell you how many moles of one reactant with another reactant will then form how many moles of the products. And that's what those coefficients in the front really are telling you. So, but the Avogadro's number allows us to tell us how many atoms are there, how many molecules are there, things like that. That's one of our conversion factors in working with the moles. So it's real important. Okay, so here, an example of how Avogadro's number is used. If you had an 85 kilogram human contains about 4.25 grams of magnesium, how many atoms are there in 4.25 grams of magnesium? The key here is going to be, we like to work in moles. So this is an example of where we use dimensional analysis to change from grams of magnesium to atoms of magnesium. And one of the key things to setting up this problem is making sure that we keep our units straight, so in our dimensional analysis, so that we're canceling the stuff out correctly so that we get to the proper units at the end. So if we're in grams and we want to get to moles, that's where we use the atomic weight of magnesium to do that. And so the atomic weight of magnesium is 24.305 grams per mole. So in our first dimensional analysis step, if we have the grams in the denominator and the moles in the numerator, we see grams of magnesium cancel out. So 1 over 24.305, that puts the moles in the numerator, the grams in the denominator, and now we can cancel out those grams of magnesium. So now we've gone from grams of magnesium to moles of magnesium. Then we know from Avogadro's number that a mole of, doesn't matter what it is, any 1 mole of anything has 6.02 times 10 to the 23rd atoms, molecules, whatever, has that many pieces, so to speak. And so we use that conversion factor, that 1 mole of magnesium will have 6.02 times 10 to the 23rd atoms in it. See here, they're using another digit past the decimal. That's okay. But what we see is by having moles in the denominator and atoms in the numerator, then we cancel out the moles from that first conversion that we did. So we've gone from grams to moles, then moles to atoms. And that's how we make the transition from expressing something in grams to atoms. And then if you do the math, you get 1.05 times 10 to the 23rd. They ask a question here of, why are there 3 significant figures in the answer? Anyone have a thought on that?
That's what you started with. That's 3 significant figures.
Yeah, that initial weight that we had of magnesium, 4.25, had 3 significant figures. Because it's a multiplication division type problem, then that is going to drive the number of significant figures for the rest of the calculation and in our final answer. So it didn't matter, for instance, that our atomic weight had 5 significant figures. It didn't matter that our Avogadro's number had 4 significant figures. That initial weight, that experimental weight we had in the beginning, drove those significant figures. So you'll hear something called molar mass. Molar mass is essentially the same as formula weight, which is the same as molecular weight. This is the number of grams in a mole of something. And we calculate that and figure that out just as we did when we talked about those molecular weights, those formula weights that we did in the beginning. All of these kind of terms have subtle differences, but essentially they mean the same. So here are just a table of some atoms and some compounds and things like that that just kind of shows you the relationship from this stuff. So one thing you'll notice is you see the formula weight column and the molar mass column, AMU, grams per mole. You see those numbers are the same. So just different ways of expressing, and there's reasons for doing that, but just I think the key thing to remember is it's all the molecular weight is what you're interested in. Except for the nitrogen, that's atomic weight, because it's just nitrogen and silver. But the other thing you'll see is over on the right, number and kind of particle in 1 mole. And so if you look at it, you see our friend Avogadro's number coming up. So 6.02 times 10 to the 23rd atoms. If we look at the dinitrogen, molecular nitrogen, you'll see that there are 6.02 times 10 to the 23rd N2 molecules, but for N atoms, it's twice that because there's 2 atoms making up that molecule. You can see kind of a similar thinking down with the barium chloride down at the bottom. So this relationship between moles, atoms, centers around Avogadro's number. The other thing is, remember, moles come as a result of molecular weights, and that's where you use those number of atoms times the atomic weight, and then sum that up to get the molecular weight. Okay, converting amounts. So this is the heart of the dimensional analysis stuff. And let's just go over this a little bit, is that moles are what we operate in most of the time, because this kind of takes us from the molecular scale to the normal world scale, and allows us to convert mass to atoms and vice versa. And here's an example of how many atoms are in 3 grams of copper. So 3 grams of copper, we'd want to convert that to moles of copper. So we would have moles in the numerator, and in the denominator, we'd have grams. So here we see 3, and then in the times 1 over 63.5 grams. Where did that 63.5 grams come from?
The periodic table, copper's atomic weight.
Yep, that's copper's atomic weight. So we could get that from the periodic table or some other list of atomic weights, and that's where that comes from. So if it was a different element, then we'd have to look up what that atomic weight was and use that. Then we want to change that mole of copper to atoms of copper. This goes back to our Avogadro's number relationship of where atoms, 6.02 times 10 to the 23rd atoms in 1 mole. So we use that ratio. So we have moles of copper in the denominator because we want to cancel that out with the moles of copper in the previous step and then get it into atoms. So first step, we're changing grams units to moles units. Then we're changing moles units to atoms units. And we see that 3 grams of copper equals 3 times 10 to the 22nd atoms of copper. This also kind of gives you a feel why we don't usually talk about things in terms of atoms very often. And it's because it would be kind of a pain in the neck to be writing 3 times 10 to the 23rd and then adding that to some big exponential number like that. It's much easier talking about moles, to say 1 mole of copper, 2 moles of copper, things like that. That's a lot easier than saying this big number of atoms. Okay, so let's do an example here. So if we have 10.0 grams of hydrogen sulfide, H2S, how would we calculate the molecular mass, the molecular weight of hydrogen sulfide? What would we do?
We figure out the atomic weight of sulfur and hydrogen and add them together.
So we need to know the atomic weights of hydrogen and sulfur, but we have 2 hydrogen atoms, so we would want to multiply 2 times the atomic weight of hydrogen. Hydrogen's 1, so that would be 2. And then we would add 1 times the atomic weight of sulfur. I don't know that off the top of my head. But that total would be, let's just see what it is. That total would be 34.084. So here we see 2 times the atomic weight of hydrogen, which is the 1 number, plus 1 times the atomic weight of sulfur, which is 32. And then that gives us our final molecular weight of 34. We said that we wanted to find out how many molecules that was. So we know that we can use that molecular weight to go from grams to moles, or whether, and so there we do that in the first step, where the units on our 10 grams of hydrogen sulfide cancel out in the denominator with the grams of hydrogen sulfide based on our molecular weight. That gets us to moles of hydrogen sulfide. We know from Avogadro's number that 1 mole of hydrogen sulfide has 6.02 times 10 to the 23rd molecules of hydrogen sulfide. So then in that step, the moles of hydrogen sulfide cancel out, and we've converted our units from grams all the way over to molecules. And so now we know there's 1.77 times 10 to the 23rd hydrogen sulfide molecules in that 10 gram sample. Okay, so there's some homework problems centering around Avogadro's number and moles. I'd like you to take a look at those. And that's where we're gonna stop for today, because there were a couple places in there where there were some homework assignments. I'd like you to take some time and have some time to work on that a little bit. So think about balancing equations, calculating molecular weights, calculating percentages. I would suggest that for the lab, go back and take a look at what I sent you and see if it makes a little more sense now. And because that's what we just talked about here today. And so that's it for today, and I'll see you on Wednesday. Thank you. And as I said at the beginning of class, it looks like if you want to attend in person both days, that's fine. I think our numbers are good. So thanks.